Hello. So in this lecture, we're going to talk about the biosynthesis of some amino acids. Just before we get started, let's recognize that we've actually been talking about the biosynthesis of amino acids kind of here and there through catabolism. And so I'm not going to cover every amino acid, certainly. But let's go through some that we haven't covered yet. So I'm going to start, I'm just going to kind of go from the book. There's a good breakdown and summary of where all of the amino acids ultimately came from. And some critical sources in there that we've seen before, particularly components of the citric acid cycle. But what I want to talk about first is I want to do the biosynthesis of serine. It's one of my favorite amino acids, and it doesn't have too complicated of a biosynthesis. But what we do in this one is we start with an intermediate that we've seen before, which is or maybe we haven't seen this one before, but it's common enough. It's 3-phosphoglycerate. I'm going to check the book here. I thought this was so this is in the glycolysis pathway. Yeah, I thought we'd seen this before, but it's hard to keep track of where all of these have come from. So, okay, what we're going to start with is an oxidation using NAD+, going to NADH. And the oxidation event is going to happen at the secondary alcohol that's chiral. We'll destroy the chirality and we get to an alpha keto acid. And this alpha keto acid can undergo a straightforward transamination with glutamate. So the natural amino acid, glutamic acid, or glutamate in its deprotonated form, gets transaminated to alpha ketoglutarate, which I'm just going to call alpha Kg. We've seen that intermediate so many times. But that's going to induce the transamination reaction. To give rise to our L-amino acid center. And then all we have to do is what is likely a straightforward SN2 reaction with water, or some sort of water is involved somehow. I'm not sure if it's an SN2 reaction or if it's a phosphoester hydrolysis. Okay, doesn't specify in the book either, but the water is going to clip off the phosphate group, and be interesting to know what like a heavy water experiment would give us in terms of if we added heavy water to this, would we see the oxygen incorporation into the amino acid from the water, or would we just lose the phosphate ester? Anyway, now we're at serine. Okay, so intercepting and this goes pretty quick then, this biosynthesis of serine, starting from an intermediate in the glycolysis pathway. Now, to switch things up in terms of the type of amino acid, the complexity, and what I would argue, the efficiency. I would wager this is not a very efficient biosynthesis, but it's a critical amino acid, biosynthesis of lysine. Okay, so lysine, when I saw this, I thought back to all of the training I've had about designing an efficient synthesis. Like if you want to synthesize something or propose a synthesis in whatever setting, whether that is a academic setting, industrial setting, you want to keep some things in mind. Like you want minimal byproducts. You want to reduce the number of steps possible. You want to, if you set a stereocenter, you want to use that stereocenter throughout. You don't want to lose that stereocenter and then have to regenerate it later on. All of these things are sort of out the window with the lysine biosynthesis. So I thought this was, it's complicated, but it's just so weird. It's kind of fun almost, especially in a class where you don't have to like take a test over this. All right, so I want to start with aspartate. So we already have our or aspartic acid, if you want to call it that, in its deprotonated form. So we've already got our alpha amino acid system put in, and we're going to treat this with ATP to do a phosphorylation reaction, which means adenosine diphosphate is going to be released. When we do this, we're going to put the phosphate group on the carboxylic acid. So that carboxylic acid or carboxylate is going to be at the delta position, or gamma position, excuse me. So just the unusual aspartate carboxylate. Okay, now this is going to be reduced. This ester is going to be reduced. This is a cool reaction, actually. But if we think about this as our leaving group, then we're going to react this with our usual reducing agent, NADH, with the H on there. That serves as the hydride reducing agent, giving rise to NAD+, which can be used as in an oxidizing transformation. We're going to add H- from the NADH into this carbonyl and kick off the phosphate leaving group. That's going to give us an unusual intermediate, an aldehyde. We've seen these a few times, and they're critical in the biosynthesis of whatever we're trying to make. So we have an aldehyde here, and that's going to do an aldol reaction with pyruvate. So pyruvate being here. Okay, so I want to think about this alpha position as my negative charge. Okay, it's not like we're going to form an actual enolate within an aqueous medium, but that gets converted into a good nucleophile or an enolate equivalent, which we could then add to the aldehyde and do an aldol reaction. Okay, when that adds in an aldol-like reaction, we get a carboxylate at the end of a chain next to a ketone. And we go down to here, and then our new bond is right here. And that gives the OH. So this is our new bond here. And in an aldol reaction, carbonyl becomes an alcohol. So there's that alcohol that results. And otherwise, everything else is from the aspartate precursor. And now what I want to recognize is that I have a nitrogen off an amine. It's not in a good protonation state right now, but an enzyme could easily take care of that. We're going to recognize that we're 6 atoms away from a carbonyl carbon. So we're going to form an imine or a Schiff base or an aldimine, depending on what you want to call it, that's got a 6-membered ring. So here is now my cyclic imine that results. CO2 minus over here, and I also have a CO2 minus over here now, and an OH up here. Okay, so what we can do at this point is an elimination reaction to kind of do an aldol condensation reaction after the aldol reaction that we did previously. So we're going to lose H2O from this to get to a conjugated diene. We're actually 2 hydrogens away from an interesting acid that's called picolinic acid. And so this is actually dihydropicolinate. And so, I mean, it's not like a critical name to know, but I mean, it's a fun name to say. So what we're going to do at this point is after we've lost H2O to establish the formation of the new bond, we're going to do a reduction of a carbon-carbon double bond using our NADPH in this case, basically NADH. And so we're going to add an H to this, and that's going to remove the double bond in the upper left. And those are the hydrogens that result. Now, one of the hydrogens is from an H+. So I guess I'll make sure that's clear. Okay, so now we're at tetrahydropyclinate. If we wanted to write that name down, Okay, what are we going to do at this stage? Well, at this stage, we're going to treat this with water and lose the Schiff base. So the water is going to add in to the imine and reverse that reaction to give back the carbonyl. Now, what does that look like? Well, it actually looks like what we have right up above that structure. So it's interesting to take a look at what nature is doing, okay? But this is the structure. Now, I want you to compare that to the structure. I'm just going to highlight it for a moment right here. Compare those structures, and you'll notice that what's changed is we've done a deoxygenation to introduce a hydrogen at this position. So we did that over 3 steps. First step was forming a Schiff base, then dehydration, then hydrogenation, and then hydration again to ring open. So we did 3 steps just to lose an OH. That reminds us, when in organic chemistry, the deoxygenation of a carbon is actually very tricky. That's different than a reduction. I mean, it is a reduction, but just stripping off an OH is very difficult. And so this is how nature pulls it off. It takes a step close to aromaticity with the dihydropyclinate, but then it backs away by doing that reduction. So by introducing some conjugation into the system, through that imine, it sort of tricks the molecule. And I guess, the conjugation was already there, but it doesn't happen until it cyclizes to the imine, which is kind of interesting. So it gets to this point where it tricks the molecule into getting really close to an aromatic pyridine. And pyridine is a very aromatic molecule, be very happy in that state. And then it backs away to get back to our ring open form. Now, from this point, we can do a transamination, and it's starting to look a little bit more like lysine. If you recall, lysine is weird. It's different than arginine because it has an extra CH2. It has 4 CH2s. It's different than arginine, which means it's different than that ornithate. Ooh, gosh, I got that name better. Ornithine. It's different than the ornithine by 1 carbon, and the ornithine, isn't incorporated that often. I don't think it has any TRAs evolved for it in native systems. So we don't see that incorporated in the proteins. It's that extra CH2 on the lysine that really gets us to the proteins that we want. You think about it, a lysine is that critical residue that helps to swing the PLP around the enzyme active site and all of those types of reactions. Okay, anyway, sorry, it's good. Got a little sidetracked there, but we've got glutamate doing a transamination to give not E, alpha keto glutarate, alpha Kg. So that transamination is going to happen at the ketone on the left side of our molecule. And the stereochemistry here is going to be S, as it's usually S. It's a pretty cool molecule, right? It's got some symmetry. If we wanted to, we could break down its symmetry. Now, it's not symmetric, but if you've taken, I don't know if we talk about point groups, but this is what we call a C2 symmetric molecule. It's symmetric over a 180-degree rotation, or C2 means circular divided by 2. It doesn't really mean that, but that's my shorthand way of thinking about it. So 360 divided by 2. Okay, so it's C2 symmetric, but it doesn't have that bilateral plane of symmetry that we really have. In fact, this is still, a chiral molecule. I missed a step in there. In the H2O and ring opening, we also add succinyl-CoA. Succinyl-CoA, which is going to make this an NH succinate, or a succinamide. So I'm just going to write SUCC, and I'm just going to cross it out. I know that's not great, but sorry I missed that step. So we don't have that perfect C2 symmetry here. But in this step, now we're going to clip that succinate off using water. So water is going to remove the succinate. Okay. In the succinamide that is formed is that dicarboxylic acid. O is 2, my is malonic at 3, Succinic acid is 4, so it's a 4-carbon dicarboxylic acid where one of the CO2 minuses is replaced with the nitrogen of an amide. Okay, so now we're back in business. Now we can like meaningfully have our C2 symmetric line here. We're not like bilateral symmetry, but if we spin it 180 degrees, we get to the original orientation. So that's how it's symmetric in this case. Okay. So what we do at this point is we get to a really cool molecule. I guess I could write the name. So this is diamino pimolate, and it is the SS version. S is both coming from ultimately from these transamination enzymes. Okay, now at this point, we're actually going to scramble the stereocenter. Well, not necessarily scramble, we're going to epimerize the stereocenter. Epimerize means to flip one stereocenter, but not all of the stereocenters. Really only one, just one stereocenter. So we're going to epimerize that stereocenter to get to a really cool molecule. The really cool molecule is a diamino acid. It's a diamino acid with 2 dashes. Look at this molecule. This molecule is nuts. This molecule is crazy. Why is this molecule crazy? Because it's meso. What the heck, nature? What are you doing? What does that mean to be meso? Well, when it's meso, it's achiral. So nature, you did this weird like 3-step cyclization. You introduced a succinate, then you remove the succinate. That's why Willoughby forgot about it. It's nature's fault. You do all this work, you establish, but you beautifully allow the transaminases to establish chirality, but then you destroy the chirality. This is achiral. If I make a succinimide on here, I have now a mixture of diastereomers because I am racemic. Or I mean, I'm kind of starting from a racemic precursor, unless you have some enzyme that selectively does it. So I don't know what you're doing, nature, but nature doesn't mind because nature's smart about chirality. Well, it's not really smart. It just can kind of brute force chirality. And what it's going to do is selectively remove one of the CO2 minuses, and only the CO2 minus on this left side. Because if we hit the CO2 minus on the left side, what we can do is get to a more familiar and friendly face to us all. But we're going to remove that we're going to remove that through a decarboxylation, that is a minus CO2, and get basically the same molecule. Well, now this molecule is chiral because the enzyme was selective about which of the 2 CO2 minuses it pulled off. It knew the molecule was achiral, but within the enzyme active site, it formed diastereomeric interactions, allowing it to tell the difference between the left and the right side within this orientation, left and right side, I guess. But anyway, by losing CO2 minus and replacing it with an H, so that we have 2 H's and we don't have a stereocenter on that left side, we now have a stereocenter. We're back to S here. Well, it turns out this is a molecule we care about. This is an alpha amino acid with an NH2, or protonated as NH3, that's 4 carbons removed from the alpha position. That is our friendly neighborhood lysine as a single enantiomer. I just thought that biosynthesis was weird. Why beautifully establish the stereocenters and then destroy them, and then destroy them both by making a meso compound? I mean, you effectively get to something that's achiral, okay? And then you just remove the CO2 minus to get the product. You could have removed the CO2 minus without destroying the stereochemistry. So it's super weird. I just loved it. I thought it was marvelous. Okay. Anyway, the decarboxylation is a PLP-dependent enzyme. So we've talked about PLP-dependent enzymes before. Here we're going to have the, we're going to select for this nitrogen to interact with PLP, and then the CO2 minus is more likely to be lost. We reprotonate, we clip off the aldamine from the PLP to release L-lysine. Okay, but this epimerizations at alpha positions of amino acids can be done with PLP, but the book states that this is not a PLP dependent enzyme, which is just super weird. Okay, it's just a really weird enzyme, a really weird strategy. I mean, you had it back with that transamination. I mean, the deoxygenation was weird, but you had it at that position. So I don't know. Okay, so that's enough of my ranting about that. Let's go ahead and let's go ahead and talk about now. Let's do. I want to do methionine. Okay, so I want to do methionine at this point. So methionine is the amino acid that has a CH3S, and it's got one additional carbon than cysteine. So it's got a sulfur atom like cysteine, but it's got that extra CH2 H3C S, excuse me. It's got that extra CH2 compared to cysteine, which makes it kind of weird. I'm really interested in what's going on with this molecule. Okay, so we're going to start with an intermediate from the previous biosynthesis, and that is aspartate semialdehyde. This aldehyde that we got after we formed an acyl phosphate and did that cool reduction where we converted this basically an anhydride into an aldehyde. Really hard to do chemically, but enzymes got it in the bag. Okay, we're going to reduce this using, it says here, NADPH. So we've got the additional phosphate there. Okay, no sweat. After that, we're going to convert the aldehyde into an alcohol. So pretty standard reduction. We could do this chemically if we needed to, or using kind of standard conditions, I mean. Okay, now we're going to react this with succinyl-CoA, which we did last time, but only at the amine here. Going to react this with succinyl-CoA. We're going to convert a thioester into an ester. The CoA is a thioester of succinate. It's a monothioester. We're going to react that with the alcohol. And this molecule is actually called homoserine. It doesn't have that dash in there, but the homoserine allows me to emphasize that here, homo doesn't mean highest occupied molecular orbital. It means just extra carbon. Not really sure where it came from, but it's pretty ubiquitous in the chemical literature. If you're talking about a structure that's fairly common like serine, and here we're adding an extra carbon, a CH2. It's usually not a methyl group like at the end of a molecule. It's just an extra carbon within a chain. We call that the homo version of the molecule, the homoserine in this case. That's important. That'll come up quite a bit as we talk about making homocysteine, which is an important intermediate in the pathway towards methionine. Okay. All right, so we're going to treat this with succinyl-CoA to make the succinate ester at the end of the chain. Sorry for those dots there. Just going to get rid of them. Trying to make my notes nicer this week. Okay. So now at this point, we have, it's fine. It's not a great leaving group, but it's good enough. Okay, so at this point, we're going to react this with a sulfur nucleophile. So sulfur is generally an excellent nucleophile, and so that's why cysteine really gets a lot of work. But here's cysteine. It looks like methionine, except it doesn't have a CH3 cap on the sulfur atom, and the sulfur atom is one carbon closer to the alpha position. So we're going to just add this to our good leaving group, the carbon bearing our good leaving group, and we're going to lose a hydrogen as a basic site, and an enzyme facilitates the deprotonation event. Okay, so what that looks like then is we have this molecule that has an alpha amino acid position here, which extends into sulfur now, because sulfur added to the carbon and displaced the oxygen. And then we have our cysteine atoms on that attached to that carbon that had the succinyl phosphate. Now this is a cool molecule called cystothione. It's an important precursor in a lot of metabolic pathways. We can give rise to several interesting types of molecules. But in particular, what we're going to focus on this time is we are going to convert this into methionine. Okay, so step 4 here. Step 4 here is a PLP-dependent enzyme, and what we're going to do is we're going to cleave this bond to give rise to the SH compound. Okay. So that's a PLP-dependent enzyme. So we're going to stabilize the negative charge here. And the byproducts for this reaction are pyruvate. So there's our carboxylate. Now the amine must get sort of, well, it's probably not transaminated, but it's just hydrolyzed with ammonia as a byproduct. Yeah, it says ammonia as a byproduct, but it doesn't give a detailed reaction. It says a similar process happened in the serine pathway. Okay, so here we're at a molecule that I wanted to talk about. Now I feel super bad about what I'm going to do, but I'm going to do a mild bit of plagiarism. I just saw this beautiful slide by an undergrad in a collaborators group, and I meant to touch base with them, but I kind of forgot which of the students presented this. But they talked about this molecule. This is why I just drew on the screen. I'll bring our notes back up here in a second. But they did this beautiful kind of discussion. I think it was Isa that presented this, or Megan. Shoot, I don't remember. I'm so bad at this. Okay. Anyway, this is just for learning purposes. We'll be quick. So this is homocysteine. A student made this slide. I thought it was beautiful, so I commandeered it. So this is homocysteine. It is toxic in high quantities. We have to deal with this. We have to get this methylated. And if you get greater than 15 micromoles per liter, so 15 micromolar of homocysteine in the blood, you get what's called hyperhomocysteinemia, which causes cardiovascular disease, vascular dementia, Alzheimer's, bone health issues. And you can actually inherit a disease which makes it difficult to process this into methionine. And so you have to take more vitamin B6. So anyway, I think we've talked about vitamin B6 in the class. Okay, let's get out of here. Let's get back to better academic conduct. I just thought that was such a great slide. And I know the student would have given me permission. I just forgot which student presented it. Okay, so bad, so sorry. Okay, here we are. So we're at homocysteine. This is bad. Skull and crossbones. Okay, all right, we're having fun, hopefully. Okay, so in this reaction, we're going to methylate this with methyl tetrahydrofolate. And that's going to give THF, which is tetrahydrofolate. It's interesting. I always thought that was done by Sam, but there's an interesting kind of trade of a methyl group from tetrahydrofolate to an enzyme with a cobalt active site, and that introduces the methyl group probably by way of a radical mechanism. Sulfur can make radicals. That's going to cap our toxic SH at the end of our chain into a methyl group to give homocysteine. Okay, anyway, I thought that was really fun. Or excuse me, that's going to cap the SH of homocysteine to make L-methionine. Okay, like start codons and that sort of thing, if I'm remembering molecular biology correctly. All right. Let's do, getting a little long-winded, but let's do threonine, and we'll call it a lecture. That seems like a good stopping point. Okay, so L-threonine biosynthesis. And for L-threonine biosynthesis, we are going to steal a metabolite from the biosynthesis of methionine. We're going to use homocysteine again. So homocysteine is serine with an extra CH2. Okay, this one's not too bad, actually. We are going to phosphorylate this using ATP. That's going to put a phosphate on the nucleophilic oxygen atom at the end of our chain. All right. And then we're going to do a PLP dependent with loss of, with addition of water, loss of PI, and we're actually going to set the beta stereocenter to make L-threonine. So I do want to go through, I haven't done too much with enzyme active sites and cofactors, so I do want to go through that mechanism, that water loss with sort of hydroxy rearrangement. So let's do it. Okay, so we are going to take our phosphorylated homophenylserine and react it with PLP. That's going to give us our external aldimine from the enzyme active site, where I show that as an imine bonded, an aldimine or an imine or a Schiff base bonded to PLP. Now what I want to do is first, I'm going to, remember the PLP can harbor, has a plus charge right now. So let's deprotonate it. We're going to go X minus here. We're going to deprotonate this. I'm going to swing that wedge over to the dash and make a double bond and then push the electrons into the PLP cofactor. So let's just get into it. That is going to result in a double bond to a nitrogen just on the opposite side of where the PLP was. And now the PLP is neutral. Okay. With the PLP being neutral, what we can do is actually deprotonate. We actually, we tautomerize actually. So this is a tautomerization where we're going to move this H up and onto the nitrogen and go from the imine to the enamine. So this is normally not favored, but with enzyme magic and PLP cofactors were there. So now we're at an enamine. So the enamine will now be able to kick out the phosphate leaving group by going like this. We're going to lose that hydrogen to remake that carbon-nitrogen double bond, push these double bonds over to break the to avoid breaking the octet rule, and then kick off the phosphate leaving group, and that's going to give us this thing. Okay. Now what we're going to do is react this with H+. Now to get to H+, what we have to do is use some of the electrons from the PLP cofactor. And maybe I can, let's draw PLP at least once, right? Okay, so PLP is upside down in this case. Now, pyridine is just such a strongly aromatic molecule that this molecule, even though it's neutral and stable, is desperate to be aromatic, desperate to be pyridine again. So we're here. Yeah, we got an OH out here, probably hydrogen bonding. We got a methyl group. We got our phosphate for molecular recognition over here. Okay, but this lone pair doesn't want to be a lone pair in its usual sense. It wants to be aromatic. So it's going to push itself over, say enough is enough, push electrons through all the way to the very end of this chain until we can pick up an H plus from somewhere. Okay, now the PLP is positively charged, but we can at least kind of see now why we would ever want to pick up this hydrogen. Now, this hydrogen is critical because it defines the CH3 at the end of our threonine chain. Additionally, now we can see why water would ever want to add into this molecule. We can, using a base or something, boom, there we go. Okay, we can add the OH and push all of the electrons back through to neutralize the PLP. And this being done in the active site means we can set that stereo center. So now I'm at PLP 0. Okay. Now we just need to kind of finish up our transamination mechanism. So here we're going to going to add our lysine NH2, and this is something we do all the time, and we'll lose PLP through a step that involves transaminations and also sets the alpha stereocenter. But that's how we add the H2O into the molecule to get the beta OH on threonine with good stereo control. Notice we had to, we didn't add any carbons along the way, but we had to kick off an OH to then add in a new OH. Okay, so I had fun. I think this stuff is super fun to talk about. We'll continue on with some more biosyntheses of amino acids and then wrap up with the biosynthesis of proteins with tRNAs and that sort of thing. Super fun. Okay, all right, we'll see you next time.